So now that we've looked at a capacitor and a battery and a resistor in series and the charging of the capacitor, we're now going to look at a capacitor that's discharging when there's no battery. So first thing I want to do is look at the equation. So I'll give you sort of the short version if you're just trying to review here. These are the results. Basically, charge, voltage, and current all decrease with time by a factor of e to the minus t over RC. So let's talk about sort of conceptually what's going on here. So you have no battery, but you do have a capacitor, and that capacitor comes pre-charged, so to speak. So at some point there was a battery, but not right now. Because of that, that capacitor has potential, and it will force current through this resistor. Now in the beginning, that is a substantial amount of current, I naught, that is going to be equal to whatever the initial voltage was of the capacitor divided by the resistance of the circuit. As time goes on, however, and you lose charge, the voltage across the capacitor goes down. Remember, the voltage of a capacitor is Q over C. And because you're losing Q, you're also losing volts. So what that does is that takes this current and that is going to shrink it. So it's going to gradually, well, actually it's going to rapidly in the beginning decrease. So I naught will be this times some factor, which is going to turn out to be e to the minus t over RC, but you're just going to have to believe me for now. We'll show you where that comes from. And as time goes on more and more and more, eventually you completely deplete the charge on the capacitor, and there is now no current. The I is just 0. So let's take a closer look at that. Again, you have a capacitor here, and that capacitor has a charge on it initially. And if you take that charge that's on it, Q naught I'll call that, and divide it by C, that's going to give you the voltage of the capacitor. And that voltage is changing as the amount of charge in the capacitor changes. You also have a current flowing through this resistor, which is going to be I. Now here I'm going to use a lowercase I because the current is changing, so I like to represent it that way. We're going to use Kirchhoff's loop rule again. So if this is the positive charge side of the battery, I'm going to draw it this way. And it's still true, even though there's no battery, that when you complete a loop in the circuit, all the energy has to be dissipated somehow. So there's sort of two ways you can look at this. The traditional way I normally see this written up is that you have a Q over C, which is sort of the voltage across the capacitor, and current leaves the capacitor, and then it goes through the resistor, and you lose IR, and that's got to equal 0. Now, much like with a discharging capacitor, or rather a charging capacitor, you can replace I with dq dt, but you've got to be a little bit careful about the signs. You've got to be consistent, and this bothers people. So in this case, we have to say I equals negative dq dt. And you may be saying, what you talking about? Why is it negative? Well, it's negative because we're saying that current in the positive direction here is going clockwise. But the dq is actually decreasing. And as you decrease the q, the I is actually going to decrease. So we need the current to go in the positive direction when the Q is decreasing. So that's why the negative sign is there. And when you put in negative dq dt times R, that of course becomes plus. So you end up with Q over C plus dq over dt times R equals 0. Now there's another way that I sometimes like to envision this, and that is that it's a capacitor that is charging. It just happens to have a battery voltage that is 0. So if we wrote the exact same thing we did in the previous video, E minus Q over C minus dQ dt R, because that's I. This is actually cool, because what it's saying is that if charge were going into the positive terminal of the battery, it would be minus, and current going through the resistor is going to be minus. It's losing energy. It's just that the battery voltage happens to be 0. So you end up with minus Q over C minus dQ over dt, or if you prefer, Q over C plus dQ over dt R equals 0. Either way, you get exactly the same thing. So whichever way you choose to view the problem, we're going to play a similar kind of game to what we did yesterday. So I'm going to choose to multiply both sides by C, and that's going to give me a Q plus RC dQ dt equals 0. I'm going to bring the RC stuff over, so this becomes Q equals minus RC dQ dt, and now we're in a separation of variables situation. I'm going to bring the minus RC over to the left by dividing, multiplying dt. I'm going to bring the Q over, which is going to give me 1 over Q dQ, and now we're in a situation again where we are going to integrate. Again, you've got to be a little bit careful with your limits. Now, time still goes from 0 to, I'm going to call it capital T. That's the time at which you want to know the charge or the voltage or the current for that matter. And the charge is going to go not from 0. Remember, the capacitor is already charged. Let's call that initial charge Q naught. And then it's going to have some final charge, Q. Now, that Q isn't a constant. That Q is just like Q of T. Like, what's the charge at the time? So the left side, again, is sort of like the easiest integral in the world. dt, integral of dt is t, t minus 0, t. So minus t over rc equals, and again, the integral of 1 over q is like 1 over x. The integral of 1 over x is ln of x. So here we have ln of q, and we're evaluating it from q naught to q. So that winds up being the ln of q minus the ln of q naught, which, using your log rules, is the same as ln of q over q naught. And on the left side, I should have followed through, minus t over rc. Same. So we need to break apart the log. The way we undo the log is by e-ing it, or exponentiating, or whatever math people call it. E to the minus t over rc equals q over q naught. Now we're really getting somewhere. So q at any time t is equal to q naught, the initial charge on the capacitor, times e to the minus t over rc. And that makes sense. At time 0, you have e to the minus 0, or e to the 0 is 1. The charge at time 0 is q naught, just like it's supposed to be. So we have the charge on the capacitor at any time. If we want to know the voltage, recall the definition of capacitance is charge per voltage, or per potential. So V is going to be Q over C. So the voltage of the capacitor is Q naught over C, e to the minus t over RC. And you may recognize Q naught over C is the same thing as the initial voltage. So what this says is that the voltage across the capacitor starts off at V naught, and then it decreases exponentially by e to the minus t over RC. Hold on, my child's crying. Sorry about that, my daughter's not feeling well. So we have the charge in the capacitor, the voltage across the capacitor. Now current, unlike for the charging capacitor, here the voltage across the capacitor and the resistor are exactly the same. For the charging, it was the voltage of the capacitor plus the voltage of the resistor equal the battery. Here there's no battery, they're in parallel. It's exactly the same voltage. So if you want to know the current, both into the capacitor and through the resistor, that is going to be just the potential over the resistance, which, by the way, is the same as I naught. So the current at any point decreases exponentially from the initial value, which is just the initial voltage of the capacitor divided by the resistor. So much like with the charging capacitor, let's take a minute and talk about T and tau and RC and what all those things mean. So here we have the capacitor discharging, and you can see all three, charge, voltage, current, are all exponential decays because the voltage across the capacitor and across the resistor are decreasing. Now, the charge, if you recall, let me just pause this and write them. So here are the formulas we just got. They each decrease exponentially. In the case of the current, it starts off at a value of E, well, not E, but V naught over R. And the voltage across capacitor is just V naught, and the charge is simply C V naught initially, and they decrease. What I want to draw your attention to is the concept of tau. This RC, even though it's ohms times farads, that's seconds. So it's a time, but what does that time mean? So time constant, if you are at one time constant, meaning let's say your RC value is 200 seconds, and it has been 200 seconds, the amount of charge that's going to be in your capacitor is going to be e to the minus 1, or 1 over E. So 1 over E is 36.8%. If you look at one time constant, I did this in terms of time constants, you can see that is exactly 36.8 for all of them. If you go two time constants, that's 1 over E squared, because E to the negative 2 is 1 over E squared. That's 13.53%. So if you look at 2, that's 13.53. This is 1 over E cubed, 1 over E to the fourth, 1 over E to the fifth. Now, for a discharging capacitor, there's nothing that follows this relationship, but for a charging capacitor, there is. For example, for a charging capacitor, it starts off at a voltage of 0 and gradually increases to the battery voltage. So that's, one place where you would see this. So let's take a minute and compare and contrast charging and discharging. So here we have a discharging capacitor. Again, in the beginning, you can see a lot of charge. In the beginning, decreases. Voltage is the highest it's going to be, V naught, and then gradually decreases until 0. So in the case of a discharging capacitor, in the end, you have no charge, no potential, no current. It actually sounds kind of hopeless. During the capacitor, you're changing the voltage of the capacitor as the charge decreases, and all that energy is going into the resistor. Actually, I noticed as I drew that I made the arrows not match. That should actually go this way. Whoops. Smaller. Good enough for the internet. And here are the relationships we just looked. Now, compare and contrast that with charging. So for a charging capacitor, you start off with no charge, no potential, lots of current, E over R, and then you end up with potential across capacitor that's the same as the battery voltage but opposite. So in the end, the capacitor actually has charge. In the beginning, it doesn't. And the voltage that you end up with is the same as the battery voltage, but in the opposite direction. In both cases, charging and discharging, you end up with no current, but for two different reasons. For a charging capacitor, you end up with no current because the voltage across the capacitor is in the opposite direction of the voltage from the battery, but there is a potential there. In the case of a discharging capacitor, you wind up with no current because there's no potential difference. There's no reason for charge to flow. There's no charge in the capacitor. It goes to 0. So if I was studying for an AP exam, and I'm not, I don't need to do that anymore, I would study these two pages. I would study a capacitor that is discharging and a capacitor that is charging. And what you want to pay particular close attention to are these asymptotes. Specifically, in the beginning, what are the initial conditions for charge, current, and voltage? and what are the final conditions for charge, current, and voltage. So I believe I have gotten to everything I promised. I hope that this is useful to somebody. And to my students, good luck on your quiz tomorrow. I hope you're taking lots of good notes. It is an open note quiz.